So you just downloaded the Unreal Engine and you're excited to create some super realistic looking materials and high-tech shaders. You open the material editor and this is what you see. You've got this main node here with sockets for base color, metallic, specular, roughness, some other inputs. But what are these things and what do you connect to them? Well, you're in luck because that's what we're going to cover today. So I have a little bit of explaining to do to get started. First of all, PBR is not referring to a brand of beer. We're talking about physically based rendering, which is a rendering strategy where we're attempting to accurately model the behavior of light. Previously, computer graphics simply attempted to mimic the appearance of what light was doing, but with PBR, we're trying to model light's actual behavior. The main advantage is that we're able to create much more realistic looking graphics with PBR than with previous methods. There are two main components to PBR, light properties and surface properties. In order for materials to look as realistic as possible, both of these components need to be correct. Light properties are mostly controlled by the game engine itself, while surface properties are controlled by you as you create shaders to define them. For most of the video, we're going to focus on surface properties, but first I want to take a minute to go over the light properties, because it's important to understand what the engine is doing for you under the hood. So let's talk about this stuff for a minute. So light comes from two types of sources. Direct light sources, where light is shining directly from the source to the surface in a single direction. And indirect sources, where light is bouncing around the environment and coming in from all directions before hitting the surface. After light hits the surface, there are two types of surface interactions we're going to discuss. Specular light leaves the surface in one main focused direction, while diffuse light is scattered and leaves the surface in all directions. There are more outgoing light behaviors, but we're going to concentrate on these two most common types today. If we combine the incoming and outgoing behaviors, we end up with four main light surface interactions. Direct diffuse is light coming directly from the source and getting scattered in all directions. Direct specular is light coming directly from the source and being reflected in a focused direction. Indirect diffuse is light coming from the ambient environment and getting scattered by the surface. And indirect specular is ambient light coming from the environment and being reflected in a focused direction. These four distinctions don't really exist in reality, but in computer graphics it's convenient to break things down this way so that we can develop methods for handling each of these. Let's take a look at some example images. This is what direct diffuse looks like. It's the most simple light type that the engine calculates. Notice that the lighting is very broad across the surface and that the areas facing away from the direct light source are not lit at all. Here's an example of direct specular. While it's slightly more expensive to compute than diffuse, comparatively speaking, it's also very cheap. Notice that the lighting is very tightly focused. It's basically a reflection of the light source shining on the surface. Next is indirect diffuse. It's the most complex to calculate because it's modeling the behavior of billions of light rays bouncing all around the scene. Because of the expense required, this type of light is often rendered offline and stored in light maps. This process can take many hours in complex scenes. And finally, we have indirect specular. Some people just call this reflections. It's also fairly complex to create this effect. Most game engines provide several different ways to create this effect, like reflection probes, planar reflections, and screen space ray tracing. The most accurate method for creating these reflections is with real ray tracing, but it's also the most expensive and wasn't even possible to do in real time until just recently. These light surface interactions are combined to create the final image. Here we can see the effects of all 4 of them on our teapot. Okay, now we're going to switch our focus from lighting to surface properties. It was important to briefly discuss lighting because the surface properties control what each of these 4 light surface interactions look like, and I'll be referring back to them as we go over surface properties. So let's jump right in and talk about these. Let's start out by talking about base color. The base color input defines the diffuse color of the surface. And it's important to understand that you shouldn't put anything into your base color socket that's darker than an RGB or an sRGB value of 20 or brighter than an sRGB value of 240. And the reason for this is if your colors are way down at the end of the dark end of the spectrum, when light hits the surface, it basically won't be reflected at all, and so you'll just end up with this jet black object, and no objects in reality are actually that dark, and so your light won't react correctly with the surface. So don't make objects darker than 20 or brighter than 240. Now, if your object is really rough, that dark range increases up to 50. So objects that are really smooth can go all the way down to 20, but if the surface is rough, it needs to not be darker than about 50. And like I said, out of range values won't light correctly. So this base color is controlling the diffuse light of your object, both the indirect and the direct light. Okay, so this is an example of a base color texture. This is the one that we're going to use in our shader that we build at the end of the video. So obviously we're making some cobblestones. What I want you to notice about this texture is it's fairly flat looking. There is no lighting included in this at all, either direct or indirect light. There's no ambient occlusion baked into this or anything. It's just broad, flat colors. And that's what base textures should really look like. They're actually pretty boring. And if you want to get best results from base texture, you should really try to go out and measure the thing that you're trying to recreate in your computer model. There's a device called Color Monkey that's kind of like a scanner, but it only scans 1 pixel. And so you can hold it up to an object and click the button, and it'll actually capture the diffuse color value of that surface. So if you have the ability to take a photo and calibrate the photo so it's correct and then use that RGB value, or use a device like a Color Monkey to capture the RGB value, that will give you the best results from your base color. And here you can see a little chart over here on the right that has some actual captured colors of real world objects, kind of showing you the range that they're in from the very darkest to the very brightest. Alright, so that's base color. Let's talk about normals. Strictly speaking, there's nothing new about normal maps in physically based rendering versus previous types of rendering. Normal maps have always been the same. And basically a normal map, what it is it defines what the surface is shaped like. So you have a triangle mesh, which is relatively simple, but if you want to put a lot more detail on that surface of the triangle mesh, you can use a normal map to make the surface look like it's a lot bumpier than it actually is. So here's an example of a normal map here, and you can see that pixels over here are kind of pointed off in this direction. This is a normal map of a sphere, so if I'm right here, the pixel is pointed straight out at the camera. Here it's pointed to the left, over here it's pointed to the right, over here it's pointed down. And these goofy looking colors are not actually colors at all, but each of these pixels is encoding the X, Y, and Z coordinates of a vector that points in the direction that you want the surface to be facing. It's really important, because these pixels represent vector data and not colors, that normal maps not be hand painted. In other words, you can't go into Photoshop and use a color picker and just like start painting a normal map, because your results will be incorrect. You need to use an established method, like baking a high resolution model down to a low resolution model in order to create a normal map. So in our example data, here's the normal map for our cobblestones, and like we said, the normal map defines the shape of the surface. So I can apply this normal map to a completely flat mesh, even a single polygon, and it'll look like its shape like lots of bumpy looking cobblestones when actually it's just perfectly flat. So each vector represents a direction, and it allows us to create a level of detail that is impossible to achieve just by using triangles. And once again, you should never hand paint a normal map. That should be done by a baking process. Okay, let's move on and we'll talk about specular. Specular is also a measurement for how reflective the surface is, or how much light the surface reflects. So here you can see a range from 0 specular up to a value of 1 for the specular. And this is a multiplier for the direct and indirect specular lighting on the model. Like I said, it defines the reflectivity of the surface when you're looking straight at it. For surfaces that are not metal, the majority of objects in the world that aren't metal reflect about 4% of the incoming light. Maybe just a little more, maybe just a little less, but for everything, that's right about where objects fall. So if you pass a value of 0.5 into your specular socket, that will give you a 4% reflection. And that happens to also be the default value. So if you leave nothing attached to your specular, it will give you 4% reflection, which is like 90, 95, 98% of the objects in the world have that amount of reflectivity. If you pass in a value of 1, what you're going to get is 8% reflective. And there are some objects that are that reflective, like crystals and those kinds of things. But generally, you're going to want to leave this at about 0.5, because 8% reflectivity is too high for just about all objects. Now, there is a really interesting feature of surfaces, and that is they're 4% reflective when you're looking straight at them. But then around on the glancing angle, where the surface is pointed just about 90 degrees from your view angle, all surfaces go up to be 100% reflective. And what this is called is, it's a Fresnel term, and that measures, or that is the a formula that increases the reflectivity as the surface goes from pointing straight at you to being perpendicular to your view. So when you pass a value into the specular socket, you are defining the amount of reflectivity that you get when you're looking straight at it, and then as the angle of the surface changes to be perpendicular to your view, the amount of reflectivity actually goes up to 100%, and that's something that the engine handles for you. Okay, so let's take a look at our example specular map here, and I said that all surfaces should be a value of 0.5. And if that were true for everything, we would have a super boring map. Our map would just be 0.5 everywhere. But that's not actually true, because surfaces reflect less in crevices. And so what you can see here is there are these little crevices around the cobblestones where there's zero reflectivity, and I've painted those areas black, or actually I've just used a crevice map. So the best way to create a specular map actually is to create a crevice map and then multiply it by 0.5. So your maximum value is 0.5, and that's reflectivity of 4%. And then in all the little crevices where the object is occluding itself, where the reflections are just bouncing back and forth and getting occluded instead of reflecting back at you, that's where you'll get values lower than 0.5. All right, so that's what goes into the specular socket. And now let's take a look at roughness. This is a really interesting one. Roughness is kind of like a normal map, but on a microscopic scale. It represents what the surface looks like at a sub-pixel level. So is the surface smooth or is it rough? So if you pass a white value or a 1 into the roughness socket, you'll get roughness that looks like this, or you'll get a surface that looks like this rather. And if you pass a value of 0, you'll get a surface that looks like this, basically super duper polished smooth. So again, white is rough and black is smooth. And it's basically controlling the focus of the reflections. So you get really, really blurry reflections with a roughness value of 1, and really, really sharp, tight reflections with a roughness value of 0. Alright, so let's take a look at our roughness map. Now the interesting thing about painting a roughness map is there aren't any technical constraints. So just to kind of expand on what I mean by technical constraints, with the base color, you want to actually measure a surface and get the correct color values and not go darker than 20 or brighter than 240. But with roughness, you're free to make this surface as smooth or as rough as you want. And roughness is basically defining the character of the surface. So if you know, for example, that certain surfaces are higher than others and therefore they're exposed to more polishing and wear, then you can make them a darker roughness value. So when I was creating this roughness map, I actually used some of the height data so that I could make the tops of the cobblestones where they would be scuffed quite a bit, less rough, and way down in the crevices I made those areas more rough. Basically what you want to think about is what is the history of my object? What kinds of scuffing and wearing and polishing has it been exposed to? And where is it going to be rough and where is it going to be smooth? And you are free to make this as cool looking or as polished or as shiny or as rough as you want to, as it makes sense for each individual surface. So this map is really artistic, and it's up to you to define something really interesting looking. All right, let's move on to our last one, which is metallic. And metallic is really interesting. I've been saving metallic for last because there's a little bit of a surprise associated with a metallic, with passing a value into the metallic socket. And that is, when you use the root node in the material editor in Unreal, it basically is a combination of two materials in one, or two shaders in one. You have a shader that defines metal objects and a shader that defines non-metal objects. And the value that you pass into the metallic socket picks if you're going to use the metal shader or if you're going to use the non-metal shader. And that's pretty cool. So I want to take a minute and talk about what that means exactly. So let's go on to the next slide, and this is a little bit easier way of explaining it. When you pass 0 into the metallic socket, your base color, what you pass into the base color socket, is going to the diffuse of the object. And what you pass into the specular socket is defining the reflectance of the object between 0 and 8%. Remember, we talked about specular. If you give it 0.5, you'll get 4% here. Well, with metallic, all of that changes. And what you pass into the base color socket is now your reflectance from 0 to 100%. So metals have colored reflections, and so you're using base color to define the reflectance of the object. And the interesting thing here is that whatever you pass into the specular socket is going to get completely ignored because you're using base color to define the reflectance instead of the specular. And the other interesting thing about metals is that their diffuse is always black. So under the hood, if you pass a 1 into the metallic socket, your diffuse is just going to be automatically set to black. Your base color is going to go into reflectance, and it has a range of 0 to 100%, and your specular is going to get ignored. Alright, in our cobblestones example, our metallic map is actually going to be completely black. We're not using this socket because, well, there's no metal on cobblestones. But if we were, whatever white areas in this map would make those parts of the surface look like they were made out of metal. Now, one thing that you want to try to avoid when you're creating a metallic map is grayscale values. Those get kind of weird because really this map should be either black or white. You're setting the surface to be either metal or not metal. And when you put it in between, like if you were to give it a value of 0.5, you would be sort of halfway in between this and that, and there aren't any surfaces on Earth that actually do that. So try to make these metallic maps either black and white. Now if there's some little blending happening in between pixels and that sort of thing, that's not going to be that big of a deal. But you're not going to want to do large gradients from black to white or things that are specifically painted gray, for example. And then there's one other thing to remember that's really important when dealing with metallic maps. So let's say that you painted your metallic all 100% white, so the surface is all metallic. Now, in your base color, you need to be very careful that you paint really nice, bright metal colors. There's no such thing as dark metal, and your base color is defining the reflectivity of the metal. So I've got this little chart here that has a couple of common metals and what their base colors should be set to. And these are measurements of the surface of these real-world metals that you can actually use. So if you were to create a gold surface, for example, like the one we have here, I actually took that value from the chart and plugged it in. So you end up with something that looks very realistically like gold, because it actually is the correct measured value for what gold really is. So again, base color, when you're using metal, it's really important to use the measured value and to keep these values bright. As I said here, there's no such thing as dark metal, and all metals are 180 sRGB or brighter. Alright, so we've been through base color, normal, roughness, and metallic. Oh, and I forgot specular. We've been through all these things. Now let's jump back into the shader editor and build a sample shader with our example textures. Alright, now that we've gone over all the basics of PBR, creating our actual shader is fairly simple. I've started out with this shader. I have my root node over here, and then I brought in my textures. Let's start out with the normal map just so that we can get a sense of the shape of the surface. So I'm going to drag my normal map over here and plug it into my normal socket, and you'll see right away that our surface no longer looks flat, but it looks like it's covered with lots of bumps. Now keep in mind that all of the rest of the sockets are currently set to default, so we need to plug in our maps in order to get correct values. So next let's plug in our base color, and you'll get an idea for what the object looks like with base color but without any of the other values. So this is what it looks like with base color and normal map, but if I disconnect the normal map, you can see that it's going to look a whole lot more flat, and that normal map really serves to bump out the surface and make it look like there's a lot more detail there than there actually is. Alright, my next socket here is metallic, And since I'm creating an object that has no metal on it, I just have a value of 0 here that I'm going to wire into metallic. And that's not going to change the surface at all. But if I did have metals in this particular model, I would need a separate map for that. Alright, my next map is my specular map. And remember, this is the map that we can mostly keep at values of 0.5, except down in the crevices where the object is occluding the reflections. So I'm going to take the red channel of this map and just wire it right here into specular. And what that's going to do for me is it's going to define the areas that are not reflective, like right along the crevices, versus the areas that are. Alright, next I'm going to take my roughness map and wire that in. And what this is going to do is it's going to make some areas smooth and some areas rough. And in my case, I've defined the tops of the cobblestones as being smooth and kind of down in the crevices more rough. Alright, so there's one last map that I have here, and this is one that we didn't talk about, but there's not really a whole lot to it. It's called an ambient occlusion map, and it's something that you can bake. So this is what my ambient occlusion map looks like. I actually modeled all of these cobblestones in 3ds Max, and then I was able to use the Arnold renderer to just render out ambient occlusion. So that's how I generated that map. And this basically is a multiplier with the indirect diffuse, so that the object is not getting diffuse reflections in areas where they don't belong. And this map actually is only applied if you have a global illumination solution baked. So it's multiplied by the baked global illumination solution, so you won't actually see any difference just here in the preview window. But as you can see, now I have all of the correct PBR values plugged into base color, metallic, specular, roughness, and ambient occlusion. And so I have an object that is physically plausible. Like we talked about in the beginning, the engine is doing the lighting part of the shading, and it's up to me as the texture artist, as the shader artist, to pass correct values into these sockets to get physically accurate materials. And if I'm creating shaders that do all kinds of fancy things, like maybe I'm making the surface look wet, or I'm scrolling things across the surface, or I'm putting moss on the surface and these kinds of things, I need to keep in mind, how do all of those modifiers contribute to each of these different sockets? Maybe I'll do a video in the future where we talk about how to make surfaces look wet with these effects. But for now, just keep in mind that when you think about, maybe there's dirt overlaying your surface, or maybe somebody's painted something on part of your surface, how do all of those modifiers affect each of these different input sockets? So you want to think along those lines when you're trying to define the appearance of your circuit, of your shader, which modifiers go into which of the various sockets. Alright, so that's the basics of PBR. I hope you enjoyed this video. We're going to get into a lot more cool details on creating a lot of different surface shader effects in the future, so if you like these videos, please subscribe to the channel. It really helps me out. Alright, we'll see you in the next video.